We're on to chapter 7, which is all about optimization. So we will be using the techniques that we've developed for finding local and global extrema in order to apply those in situations within the context. There will be some simple optimization problems concerning mostly various shapes, as well as realistic biological problems requiring a bit more interpretation at the end. Let's start with just thinking about what is an optimization. What does it mean to optimize something? To optimize means to find whatever is best. Best will depend on the context, and generally there are a series of steps that one should follow in order to really be able to set up the problem mathematically and then tackle it. First of all, because the problems will be word problems, we will need to identify all given quantities and assign variables to them. The thing that helps a lot here is, in fact, to sketch a picture where possible. Just like before, the graph is useful not in just visualizing things, but often in determining what are the important quantities. The second step here would be to construct the objective function. Objective function, that's what we call the thing that we're actually trying to maximize or minimize, whatever it is, what you're trying to optimize. After you've done that, oftentimes your function will have more than one variable in it, and we'll see an example in just a little bit. So what you have to do is figure out potentially other relationship between your variables, so your optimization objective function only has one independent variable in it. Once you have all of that down, so once you have a function that depends only on one variable, then it's just calculus techniques that we've discussed in chapter 6. So let's take a look at the very first, simplest optimization problem. I titled it, which rectangles are best? Again, it really depends on what your definition of best is. And in this first slide, I am looking to find rectangle of a fixed perimeter, 100 meters, let's say, with maximal possible area. This really is a fairly realistic problem. Let's say you have a fixed amount of fence and you're trying to enclose as much land as possible. My friend Paul, for example, actually did have to apply calculus to build a coop for his chickens, and we always think that it's such a stereotypical mathematical problem, but it actually happened to somebody I know in real life. So first step is to draw a picture, because once again, it will actually allow you probably to figure out what the necessary quantities are. So I'm after rectangles. So let me draw a little rectangle. And I know that it has to have perimeter of 100. So I need to know something about the total amount of side lengths here. What I'm trying to maximize here is all the area that it encloses. So what are some of the variables that will describe my rectangle here? Clearly, length and width are good things to assign to it. So let's say, well, I guess if anything, this is length and this is width, okay? And so then let's write out what is it that we're actually trying to optimize. That's when you look for words like maximum or minimum, or what is it that is important to you in this problem to make as small or as big as possible. So the objective function here will be the area function. The area of a rectangle is length times width. And here is where we see the first problem. Just like discussed on the last slide, our objective function is the function that we will then like to take a derivative of, find critical point, and find eventually local and global maximum. But the problem here is it has two variables. I don't know how to take derivatives of a function with more than one variable, okay? So we have to get rid of one of those variables, and we're going to use what we call a secondary equation for that purpose. Secondary equation will be an equation that somehow presents another relationship between my two variables here. So there is still a piece of information in this problem I have not used, and that is the fact that the entire rectangle has to have perimeter of 100. So perimeter is all the way around, which means that 2w plus 2l is what composes 100. I'm now going to solve this equation for one of the variables and then use that to replace that variable in my objective function with. Generally, there might be some considerations as to what variable is better or easier to solve for. This equation is very symmetric for L and W, so it really doesn't matter. Let me solve it, for example, for L. So I'm going to divide everything by 2, first of all. And then from here, L is equal to 50 minus W. So I can use this to plug in for L in my objective function, which will result then in my area being 50 minus W times W. Or if I want to open up the bracket, 50W minus W squared. And this is the function that I'm going to want to maximize. Okay? After this, it's the standard calculus tools from the previous chapter. So what we're going to do here is take the derivative of the function, find the critical points, and then analyze those. So in order for me to find critical points, let's first find the derivative. In this case, it's fairly straightforward, 50 minus 2W. So critical points, I need to set the derivative to be 0. And I need to consider when the derivative does not exist. So in the first case, the derivative is 0 at 25. And it does not exist nowhere because it's a nice polynomial function, so I have no solutions there. So I only have one critical point. And now there is a number of ways to proceed. You can use the first derivative test or the second derivative test. You can also find endpoints and plug those in. This is completely up to you. And in fact, every problem will probably have one of the methods being the quickest or more efficient, but there's also methods that you will be more comfortable with. So from here on, you can find endpoints, you can use the first derivative test or the second derivative test in order to actually find your global maximum, okay? So figure out which way you would like to proceed. For those who would like to think about endpoints, in this case, we're not given the actual exact interval. We have to figure it out ourselves, which is probably why some people don't like the endpoints method. You would then have to think about your variable here, which is W. What is the smallest and the largest that W can be given a constraint that all the way around your perimeter still has to be 100 and that you're trying to maximize the area, right? So the simplest thing I can say about W here is that it has to be greater than 0, but that doesn't give me the biggest value that the W can be. Okay, so what I strongly recommend here is to actually apply either one of these methods to find the maximum of this function, the global maximum of this function. Okay, feel free to try all 3 of them. I think this will be a wonderful exercise. It does turn out to be that this critical point is the global maximum. Our conclusion is that the rectangle with the largest possible area has width 25. What is its length? Well, all the way around was supposed to be 100, right? And so I can also even use this equation to solve for L. So if W is 25, 50 minus 25, it will turn out that L is 25 too. So the best rectangle is a square. Now, of course, that depends on your definition of best. In our case, it is the most area for the least amount of perimeter. So out of all the quadrilaterals, which means shapes with 4 straight sides, square will have the most area enclosed in it. And that's true in general. These kinds of problems have an inherited symmetry. The shape that is most symmetric will have the most area in it. So out of all the triangles, an equilateral one will contain the most area, and so on. So the polygons, so shapes with straight sides that have all equal sides, are called regular polygons. Now, what if I'm not constrained to using 4 sides? So what if I have fixed amount of perimeter, but I can use as many sides as I want? Which one of these shapes will now have the most area enclosed within it? Is it a triangle? Is it a square? A pentagon? A hexagon? It doesn't take very long to persuade yourself that the more sides, the better. So in fact, something much closer to a circle will include the most amount of area for the same perimeter, okay? Now, a circle, of course, is not a polygon, but if you have lots and lots of sides, that's a pretty good approximation of a circle. So circles are great for a number of reasons, but they're terrible for one particular reason. What if I don't want to just build one pasture to enclose my animals in? What if I want to build a few? Circles, while they are the most efficient in terms of area for the perimeter, are terrible at packing, right? So if I did have a bunch of circles, you'll notice that I'm actually wasting quite a bit of space because there is going to be inevitably space between them that I'm not covering. So I'm losing out my field area by having these gaps between the circles. That's why polygons, so things with straight sides, are good, because straight sides can go against straight sides and guarantee that I don't actually lose any shapes. Now, this actually gets to the bottom of a really deep mathematical result that was only proven a few years ago, that there are only 3 shapes that what we call tile plane without gaps. So out of all of these regular polygons, there's only 3 that I can pack together tightly without producing any gaps whatsoever. And the shapes are the triangle, the square, and the hexagon. Now remember, what we've discussed just now is that in this lineup, the more sides, the better, because the more sides guarantees larger area enclosure for the same amount of perimeter material. So out of all of these 3 shapes, the one with the most sides is, of course, a hexagon. So this is the most efficient tiling for the least amount of work in producing of the actual sides. Now stare for a minute at this tiling. What does this remind you of? Where do we see this in nature or otherwise? To me, this looks like one very particular thing, and that's a honeycomb. And in fact, the mathematical result I've just mentioned is called the honeycomb theorem. This is the most efficient tiling, and that is the reason why bees use it. It uses the least amount of material to produce the most amount of area, and it doesn't waste any space in between their little cells. So the conclusion is bees know math.